me this opportunity to speak, to talk about our work. And this work is done in collaboration with Nayan, who's a student here, and my long-term friend and collaborator, Tsunke and Meng from UCSB and Yale. So these two are the main references of the talk. And then, so the title says conjugates composite Fermi liquid. So we're going to take this as a parent state and get all kinds of interesting quantum behaviors from here. And of course, the session is entitled non-Fermi liquid. So I'm going to get some quantum bad matter from here, which is definitely something that is non-Fermi liquid. I'm going to try to talk about superconductors based on this state, which is definitely not Fermi liquid, and this is really, really not Fermi liquid, okay, which is an insulator. All right, we'll get there. So, right. So let me set the stage. Just to be concrete, I'm thinking about Moiré transition metal dichalcogenide, TMD. Really, just to be very, very concrete to set the stage, I'm thinking of this is one realization. You have two layers of TMD material with a twist angle. This is a picture in real space. You have these nice Moiré superlattices. And if you go to K space, you would find that the low energy degrees of freedom are all localized near the K and K prime location of the original Bourian zone. So these tiny hexagons are the Moiré Bourian zone. And due to very strong spin orbit coupling, the Ising type of spin orbit coupling, the K valley and K prime valley, the valley indices are strongly locked to the spin degrees of freedom. So I have very little degrees of freedom to worry about. You could talk about either just spin up or down, or just K versus K prime. So that's very different from graphene-based Moiré setting. And these two valleys or spin are related to each other by time versal symmetry, right? This is really, just conceptually, if you look at this picture, it looks rather simple, but it's already giving us a very good platform for amazing physics to happen, because you could go do by now, the standard continuum calculation of the band structure. And of course, you have to put in some model parameter, and you can vary various of things. For example, if you just vary the twist angle, this is a plot lifted from this work that did the numerical study of the band structure. You can see that the band structure can vary a lot, but what I would like you to focus on here is that there are lots of bands with these plus minus 1 here. They are the Chern number of the bands at a single valley. And of course, the entire system is time versal symmetric. So when one valley shows Chern number 1, the other valley would have a corresponding band with Chern number -1. So the whole thing is still time versal invariant. And for us, the terminology, for this talk, the terminology would be that these, the bands in here and here form a conjugate pair of Chern bands, right? So if for some reason you end up filling only one of these, then you would definitely get, you go to a valley polarized situation and you end up filling one of these bands, you would get a Chern insulator. This type of thinking is at least conceptually very similar to all the Chern insulators discovered in Moiré settings, where you basically have some mean field order, and after the mean field order develop, you end up filling integer amount of bands with a total Chern number that is non-zero. And conceptually, that's how you would generally get a Chern insulator from Moiré settings, right? It's not restricted to just twisted bilayer, homo bilayer like this. Other settings also give you similar physics. All right, so I just talk about integer filling, and of course, I think, if you compare that to fractional quantum Hall physics, by default, you would assume that, well, okay, if you can see integer Hall effect at integer filling, then at fractional filling, then, it's very likely that you see fractional quantum Hall physics. I guess that's the expectation for a long, long time. Until last year, it really came to life, as in people do find that, in this specific setting, twisted bilayer moly ditelluride, for certain angles of twisting, and then you could actually, you don't need a magnetic field. You go to fractional filling of these bands, and then you find out that, well, the RXY actually follows a quantized plateau. And then this state is coming out of a spontaneous breaking of the valley symmetry. So, you end up only filling one valley. And that's why you could actually get a chiral state from this setting with, at the single particle level that is time versal symmetric, right? These fractions are actually familiar ones. This is kind of like, the 2/3 filling of a single Landau level. This is like, 3/5 of a Landau level, right? So you can see that from here that you see these tiny plateaus showing up here at these right fractions. If you look at the half filling, it's not entirely clear just from this plot what that would be, but it's very suggestive based on this experiment and the numerical simulations based on these work. Actually, you would find, it's very likely that you would actually find a composite Fermi liquid right over here at half filling. Okay? So these are all very amazing results. But I think it immediately triggers a question because all of these states have direct counterpart in fractional quantum Hall physics, things that you can find in 2DAG, two-dimensional electron gas. So the natural question would be that are there anything that is completely beyond the fractional quantum Hall physics that you would find in two-dimensional electron gas? All right, so with that, I would like to transition to a proposal of ours, which is the, take this as the starting point. I'm going to talk about the conjugate composite Fermi liquid, which is, remember that in the previous setting, all of these is based on the physics, based on the term band with valley polarization. So here, I would like to start with a scenario where, I start with a system that is valley unpolarized, and I pick a specific filling to start with, which is a half. All right, so what I'm really talking about here, imagine that there are some Chern band with Chern number 1 at valley k, some Chern band with Chern number -1 at valley k prime, and I want each of them to be at half filling. That's what I meant by half-filled conjugate Chern bands. Conjugate really means these two are time reversal conjugate pairs. And then if I'm not worrying so much about this very interesting quantum geometry in these bands, I could loosely just treat each of these as a Landau level. And then I can think about what can happen in this setting. And one of the possibility definitely out there is that each of these bands basically form a composite Fermi liquid. So this is actually our starting point. We want to take that as the parent state and think about what can come out of that parent state. Okay. If you're not familiar with the composite Fermi liquid, don't worry, I will explain to you what the Lagrangian look like. But the point is that we want to think about a standard composite Fermi liquid in this valley and a time reversal conjugate in the other valley. Okay, and then for those of you who are familiar with this business, there are different types of composite Fermi liquid one can consider. There's this classic HLR composite Fermi liquid, and there's this very interesting proposal by Son, the Dirac type composite Fermi liquid. So I'm going to focus on the latter, but a lot of what I said actually are going to be the same, whichever one that you're going to pick, right? So just a bit of an introduction of the composite Fermi liquid theory. So this is still the setting that I'm thinking about. Cartoon there is really just here for visual and memory. And I would like to start talking, I would like to clarify that I would like to start with, of course, a system with, charge conservation, obviously, that should be included. And I would like to also start with a setting where I have also spin at Z conservation. So that means I could also say that this conservation is coming from the conservation of the valley quantum number. The number of particles here and the number of particles here are separately conserved. Okay, so and indeed there are good evidence in these Molly-based heterostructure that the spin as Z is really a good conserved quantity. So this is actually a good starting point. And of course, these two are related from each other by time reversal symmetry. Okay, and now the Dirac type of composite Fermi liquid follows this type of theory where I have psi1 type composite fermion called psi1 in valley K, and psi2 is the composite fermion in valley K prime, right? So this is the Lagrangian of the composite Fermi liquid, the Dirac type composite Fermi liquid by Son. So this bit is describing, before you worry about the little a, the dynamical gauge field, this bit is just describing the dispersion of the composite fermion psi1, and it follows a Dirac spectrum, and it's not at charge neutrality, actually it's at a finite filling. Actually that filling is determined by the flux per unit cell. okay? And then, of course, this is not just a free composite fermion, it's coupled to a dynamical gauge field, little a. What is a capital A? Capital A is basically the external electromagnetic field that couples only to this sector of the electron, okay? It's a combination of a global electromagnetic gauge field, and here I'm putting in a spin SZ gauge field as also a probe, okay? And you do basically the same thing for the other valley, and that's the Lagrangian for the composite fermion in valley K prime. That's the subscript, right? So we choose a formulation so that this bit of the dispersion, the dispersion itself has the same exact shape for psi 2, except that it's actually, the Fermi surface of the psi 2 is actually below the Dirac cone. So this is kind of like a particle-like Fermi surface for psi 1. This is a hole-like Fermi surface for psi 2, which actually is going to be relevant later, all right? So please remember that, I'm going to sometimes use these cartoons as a representation of these Lagrangian. Okay, good. So what about these states? And I would like to first tell you that you can actually get quantum bad matter behavior from that kind of composite Fermi liquid as a parent state. Okay, so to talk about what bad matter is, I think it's very good, or it's probably inevitable to start by talking about the classic mod Eufy-Rigo limit, MRI limit of Fermi liquids in 2D, right? So it basically follows, these very simple heuristics. If you want to think about a semi-classical expression of a, just basically the Drew theory of conductivity, the longitudinal conductivity follows this very simple expression, density electron charge square over effective mass, and then tau is the mean free time. And if you convert the mean free time into mean free path, you just have to divide that up by the Fermi velocity, all right? So this is just simple Drew theory. And if you want to go to low temperature and have this behavior, this type of formula to be consistent with the Fermi liquid theory, you better want the particle near the Fermi surface to have enough mean free path to know that it's actually a plane wave. So hence, you want Kf times L to be not smaller than 1, right? So that it has some room for oscillation. And that basically says that L cannot be too small. Otherwise, this kind of line of logic would actually break. So if you just literally plug this back in and do some conversion, of course, the density is also related to Kf. You get this very nice bound, which is saying that the longitudinal resistivity has an upper bound, which is upper bounded by this universal unit of resistance. And of course, this is a sort of a loose bound. There could be order 1 factor here, but I think the main point is that your rho shouldn't go too far away from this limit. Otherwise, at least the classic picture of Drew theory plus Fermi liquid theory is going to fail in some way, right? Then, of course, why do I mention that? Well, bad metal is a metal that is supposed to break the MIR limit. And of course, historically, when it was introduced, violation of the MIR limit is one of the properties needed, and there are other concerns about how rho XX depends on temperature. For the sake of this talk, we want what we call a quantum bad matter. Really, we just want to find a state whose low energy resistivity is finite, so it's conducting, and it breaks the MIR bound. And I'm not going to worry so much about the other properties required historically. For example, the temperature dependence. I only want to focus on the the low temperature resistivity for this discussion. All right. Hopefully, I clarified the language here, and this is what I'm going for. Okay. So let's talk about 2 scenarios that comes up when it comes to bad matter behavior. And actually, the first scenario, it's not even an example. I would say it's kind of a non-example, but it's actually helpful for a later discussion. So if you try to think about say, for example, a setting where you have disorder, that it has been studied quite a bit. This is a phase diagram, a very loose phase diagram, cartoon phase diagram for, two metal insulator transition driven by disorder in, say, thin films with disorder and magnetic field, right? Normally, people probably don't draw the phase diagram like that, but you can imagine that by tuning disorder, you could start from, it's a good metal with very small resistivity, and you gradually walk up, to this point where along the way, the resistivity increases until it hits some value that is roughly h over e squared, and then it would just jump right into an insulator. It would skip the entire region that is dot, dot, dot here. If you can actually go over here, you would actually get the bad metal, but okay, that's what's really happening in the experiment. You just gradually go here, hit some critical value, and then you just jump right into an insulator. So the bad metal region, if you will, is completely skipped from this picture, right? But to remember this, I'm going to use this actually later for our purpose, right? Of course, this is a classic example where we do know that bad metal can exist. You can have, this is data for LSCO. You have, this temperature dependence of the resistivity that just shoot through the MIR limit as if there's nothing here. And of course, this is, even though this is like 500 K, but this is still well below the Fermi energy, so it's still considered low temperature, right? So of course, this is not an example, and this is a rather complicated example, so what am I going with that? I'm gonna not try to solve this mystery. I'm trying to make use of this phase diagram and see if I can do something to turn this into a scenario where quantum bad metal can exist, all right? So actually, it's nice to actually draw inspiration from the idea of duality. So from the phase diagram that I showed earlier, this one, it seems like conceptually it's easy to think about states with small resistivity than large resistivity. Large resistivity is what we wanted. However, it's not giving us that from simple theory, but we do know of a mechanism where we can actually start from a low resistivity state and get to a high resistivity state. That's the idea of Bose-vortex duality in two-dimensional bosonic system. So you do this classic particle to vortex duality, and you will find out that actually the resistivity of the bosons, which I call rho B, is related to the resistivity of the vortices via this very simple formula. But of course, depending on what setting you're doing it in, the bosons could be charge 2, charge 1. So I'm drawing a squiggle here. But loosely speaking, the two form a product that is at this value. And that basically means if one of them is big, the other is going to be small. All right? So ideally, if I can use this formula and apply it to a fermion system, this phase diagram, well, it seems like the job would be accomplished. Meaning that I'm not going to imagine this is the real metal of the electron, but somehow if there's some vortex metal over here that is highly conducting, meaning low resistivity, then using this formula, I would naively applying this formula would bring me to a region where the resistivity of electron is big. And I'm going to skip completely over, skip this entire region, which is fine. And over here, the vortex insulator would actually become a superconductor for electron, because obviously I would get infinite, zero resistivity for bosons, if you, for the electrons, if you naively just follow this formula. Okay, so let's see if this phase diagram can be really realized. And as it turns out that, for me, the composite Fermi liquid is sort of the idea to kind of realize this setting. Okay, so the key thing that I need here, of course, is to basically put the particle vortex duality into the setting of, Fermi liquid. And definitely I need fermionic vortices, right? Vortices for electrons. And indeed, that's exactly what composite Fermi liquid gives us. Because if you just take even just the one copy, not the conjugate version, just one single copy of the composite Fermi liquid, let's just say I take the Son's theory. This is the Lagrangian. You can easily do an equation of motion calculation and show that the density of the composite fermion, psi dagger psi, equals to dA, the external flux. So that already tells you that these psi's are actually the vortices instead of the actual electron. So that's good. It seems like that's exactly what we need. So do we get, bad metal? Well, of course not, because we know this thing so well. But still, it's worth looking into what's going wrong with this theory in terms of getting a quantum bad metal. And, well, here is the resistivity tensor for the real electron. well, you get these diagonal components. These diagonal components, the rho psi is the longitudinal resistivity for the composite fermion, which is really just coming from the dispersion. So that bit is good. Had you erased all these off-diagonal terms, it's literally the formula that we wanted, right? Rho psi inverse give me rho e of the electron. However, there's these off-diagonal terms, and they should be there because they capture actually the Hall response of the liquid. And if you really try to look into the theory and ask where it comes from, oh, this is for this part. And then if you ask where the off-diagonal comes from, it comes from here, and also comes from really the Berry phase of the composite fermion near the Fermi surface. So both of these contribute equally. This and here give you this 1/2. Okay, so it's really this 1/2 that kind of make it not work for us, because if you look at the longitudinal component of this matrix, you would find that there's some combination like that, which actually is upper bounded by h over e squared. So not a bad matter. You cannot go over this limit in this setting. Well, however, it kind of gives us a sense that if somehow we can get rid of these off-diagonal terms, it would be nice. Okay, so let's move to the the conjugate Fermi liquid, where I basically have that theory twice, except, okay, there's some difference between the filling and the filling of the composite fermions. Well, that's fine. We can still do the transport analysis, but here I would like to emphasize that both charge and spin are important quantities because they both would contribute to transport. And let's just say that I assume both of them are really, really well conserved, which is kind of true from the experimental data from Jian-Fai's lab. So if you really want to deal with transport involving both charge and spin, then your conductivity tensor or resistivity tensor would be more complicated. You have to think about both the charge transport and spin transport. Instead of a 2x2 matrix that just captures charge, you actually have a 4x4 matrix. This block gives you the charge transport. This block gives you the spin Hall effect, because now we're sitting in a conjugate pair of Chern bands, so it's natural to imagine that something like that. This block is non-trivial, and of course this block is just purely spin transport. Okay, again, similar story. Had we erased all of the off-diagonal block, this is exactly the type of formula that I've been wanting. Here I normalized the unit so that everything, is dimensionless. But it's the off-diagonal block. It's really physical. It captures the spin Hall effect, but it's also the same thing that limits the longitudinal component of rho xx. So if you just work with that, it doesn't quite work. But again, yeah. Oh, well, here I'm assuming that everything is isotropic, so xx equals to yy. Yeah, that's right. Thanks for the question. And then, but again, I would like to emphasize a little bit that, in an actual experimental setting, it's very difficult to measure spin current. So why do I bother to, include that in the conductivity tensor or resistivity tensor? I would argue that this is actually a really physical setting to, physical thing to do, because if you think about, let's just say, imagine I'm doing just two terminal transport, but the argument holds. Even if you're running electrical current through this direction, let's just say that these are the voltage lead and also the current sources. Well, because of the spin Hall effect, initially you would drive a initial period of spin current in this direction, and you will end up having spin accumulation on these two edges, making the chemical potential for spin effectively different on these two edges. And the chemical potential for spin has to build up to a certain point where you basically stop all of the spin current running in this direction, right? So if as Z is hard to relax, which is actually true from these type of experiment, then so long as spin Hall effect exists, you do have to worry about the whole conductivity tensor. You cannot just say, I just choose to only look at the charge block of the resistivity tensor. All right. Well, but that's kind of giving us a hint how to get around that thing. I just want to somehow get rid of the off-diagonal block, or get rid of this effect coming from the spin accumulation. And one way to do it is, let's just say that if the composite Fermi liquid is sitting on top of some superconductor of spin, which is basically an XY magnet, then, well, and in the spin transport, you also have basically infinite spin conductivity in this block, which is the block for spin transport, diagonal spin transport. And you will find out that the effect coming from here are basically completely erased. Or in more physical terms, it means that if you have a spin superconductor, then the two edges are short circuit. There's no chance that they have any sort of spin accumulation, and our goal is achieved. The spin Hall effect is not going to bother us, and the longitudinal charge component of the conductivity, resistivity will actually follow this formula that we've been trying to get. And if you do have a good metal, good conductor for vortices, then you would get a really bad metal for electrons. Okay, so that's one type of a method to get the quantum bad metal behavior. Another way to get it might be even simpler. I don't even need a Ising magnet in the bulk. Another way to think about it is that, well, I just need an in-plane field turned on, okay, in the in-plane direction. Why would that help? Because remember the spin and Valier law. Okay, if I turn on an in-plane field in the bulk, it doesn't actually do anything in the bulk because K and K prime value has a finite momentum difference, while a uniform magnetic field cannot supply this momentum transfer, so actually it doesn't do anything in the bulk, right? However, on the edge, the momentum conservation that separate K and K prime is completely killed by the edge. Usually it's dirty, or you just have to choose the right orientation, and then the in-plane field will basically able to relax the spin only on the edge. Once you have that, it's kind of like for spin, it's grounded, you know, the upper edge and the lower edge. The spin Hall effect is not going to come to bother us. Essentially, I'm just saying that the off-diagonal block that hinders our analysis is not going to be effective, and we again get this behavior, right? So this is sort of how we can get to a quantum bad metal behavior from various of setting, and of course it has other consequences. For example, I was mostly thinking about zero temperature, but if you go to finite temperature, you will find out that because the vortices are the composite fermion, the classic gauge field, based calculation tell us that the composite fermion has a resistivity that grows, as a function of temperature, and that means actually the resistivity of electron actually decreases a bit over, at finite temperature. So maybe you want to call it a bad metal, or maybe in a sense, based on the temperature dependence, you could call it also a failed insulator because, resistivity actually decreases as you increase temperature. And there's some interesting violation of the Wiedemann-Franz law, right? I'm going to skip this and then quickly talk about the other two things I really want to mention before the end of the talk. So, of course, this is a very interesting metallic phase, and it's actually closely connected to a superconductor that could happen in this conjugate pair of term band and half filling. Because again, let's look at this phase diagram. I was mostly talking about what's happening in here. And then, well, this is also interesting. It seems that if I can get the vortices to become a super insulator, then I would get a superconductor for electron. And from picture, you can already guess what I'm going to do because this is a Fermi particle-like Fermi surface, and this is a hole-like Fermi surface. If there's any sort of inter-valley exciton or hybridization between the two exciton, then I immediately gap out the band structure of the vortices, and then I would just get a superconductor for the electron. And if you run the math, it's the same thing. As in, if you turn on this tunneling, then the two gauge fields are Higgs, and then some derivation will tell you that this is going to be a superconductor, right? If you are really careful about these quantization of these gauge fields, you will find out that actually A is not properly quantized. So this is not actually any weird superconductor. It's just a standard charge 2e superconductor. Maybe what's interesting about this theory is that if you look at this term, it tells you that any vortices of the superconductor actually traps a quantum SD quantum number that is actually a fractional unit. Here, h bar over 2 would be the amount a single electron can carry, but this guy is somehow fractional, what a vortex would carry in a superconductor. All right, So last thing I want to talk about, oh yeah, I should mention that Yahui considered a similar scenario in an earlier pre-pre as well. Okay, and the last thing I want to talk about is this really not superconductor. Sorry, yeah. Okay, I'm gonna wrap up in 2 minutes, yeah. It's this really not Fermi liquid that I want to talk about. So recently there was some very amazing result coming from Jian Fai's lab that they found a series of insulating states, but to me the most interesting one is in this setting at filling 3, they basically find something that is a fractional quantum spin Hall effect. And there's a lot to decipher here, but point is, if you modulo out the integer filled band, you are left with a pair of half-filled term band. And then it's half filling, but apparently the transport is in favor of an insulating state with a fractional quantum spin Hall conductance a half. Here I normalize the unit so that 1 is for the standard topological insulator, the non-interacting one. And then there's a whole bunch of symmetry in this system, charge, spin, and time reversal. All right, so you may ask, well, this is interesting, but it's an insulating state. How is it related to the composite Fermi liquid, the conjugate composite Fermi liquid I was talking about? Well, this is one way to get it. You start from these two composite Fermi liquid. Each of them can go through a pairing. So you would get actually this is a so-called pH Pfaffian state for K valley. It's time reversal conjugate in here. If you further do an exciton condensation, you would get to a very interesting state that we propose that is that we think is a very strong candidate for the gap state that was observed. Right? We called it the minimum fractional topological insulator that actually has a Z4 topological order. Okay, there's a lot going on here. I don't mean to give you another talk about this, but let me just list the key points. So it's fitting to call it a fractional topological insulator because of the transport, but what's minimum about it? It turns out that this topological order, this Z4 topological order, has the minimum amount of anyons with all these symmetries and the right transport. And well, okay, let me skip that, but it has some charge E/2 excitations. You can measure them via different techniques. And then this is only one way to get to this type of fractional topological insulator. There are many other ways, including this very interesting method that we call topological bootstrap, meaning that I don't have to go through all these construction. In fact, I could literally just use the symmetry and the transport to, from ground up, construct this state. So this is kind of a very unique state that could explain the experiment. All right, with that, I will leave the summary and thank you for your attention.
Thank you. Question about the superconductor.
Yeah.
So for the just usual one half state, not one half minus half, there is this exciton condensate, and the people have argued before that you have long range Coulomb interaction, and actually this effect for any separation of the layers you get this excitonic stability.
Right.
Can you just tell us what the corresponding story here is for the superconductor?
Well, so first of all, the energetics could probably be different because you're talking about a 2-component quantum Hall scenario, right? So
one half, and this is like one half minus half.
That's exactly right. Yeah. So I don't have really a lot of intelligent things to say about that, the energetics. Yeah.
Looks like for the one half, the short range PhD of this is A plus channel. Sorry, A minus channel, and the long range one from Coulomb is in the A plus. So then you get attractive interactions, so you get the pairing instability. But for this one, it's the opposite.
Yeah. So that's right.
So it's predominantly repulsive. So then I presume you don't have the pairing instability to worry about.
Yes, that's right.
Yeah.
exactly just out it gives you like the instability.
Yeah, so one other thing to add is that there could be a bare interaction between the density of the composite fermion. So let's just say if I'm not worrying about gauge field effect, they would open up the gap immediately. That would make it seem like it's an infinitesimal instability, but the shape of these Fermi surfaces might be different, that's one thing, and then the gauge field effect may require the finite interaction strength for the exciton condensate to develop. Yeah, so, right, I thought you meant the actual 1 over r squared Coulomb interaction.
Thank you. My time? Yeah. Actually, I have two questions. One is, at the beginning, you have this composite fermion. You have said each valley is filled by half.
Yeah.
Usually, when you have Coulomb interaction, because Hund's rule,
that's right.
You know, things like to polarize along the
Indeed,
one
yes.
valley.
Yeah.
What's the difference here? So you can avoid this Hund's rule.
Well, again, this is about considering energetics. And for example, I could kind of ask the same question. Why would this scenario not be a valley polarized scenario?
Yeah.
Well, okay, here, experimentally, it was found that there's no sign of breaking time reversal symmetry from here. So
maybe is that related to this this valley correspond to a very small momentum difference? So there, the sublattice have a big size. Is this kind of Murray pattern? You know, when for the particle in different valley, do they have different real space location?
They
if using Wannier function,
well, there are some Wannier function, and then they basically are localized. Well, I'm going to go all the way back to the front. Yeah, they're basically localized here. It's kind of like an internal degrees of freedom. Yeah,
but the two valley localized same place?
Roughly speaking, yeah.
Oh, I see. Another question about this minimal topological insulator is
right.
that so topological order is that what is input? What is important input?
What is the
usually?
input?
So you say you mentioned symmetry.
Yeah.
If just ordinary internal symmetry, you may have a trivial symmetric product states.
Good point.
So here, symmetry should be some strange feature. So make that. Yeah.
Yes. So here maybe
yeah, what is important? Yeah.
Right. Exactly. So that's a very good question, and I did not get a chance to explain what this is. It's just one line, but the idea here is that you have a fractional transport that is part of our input. It's kind of like Laughlin's flux threading argument. If you see 1/3 Hall conductance, you know something is interesting going on, as in you can thread a 2π flux, you know it must be an anion, it cannot be a local object, right? So yeah, this what we call topological bootstrap is literally just keep running this type of argument plus consistency of topological order. It would just bring you to this.
So the key input is you have U1 symmetry and some fractional response.
Exactly, both U1 actually, yeah, spin and charge U1, and then the transport. I just take these as input data and turn the crank of flux attachment plus other consistency charge. Yeah.
Probably this is something very basic.
Yeah.
So your composite thermal liquid has finite resistivity at finite temperature.
Yeah.
What is the mechanism of current relaxation?
What is the mechanism for current relaxation?
Yeah.
Oh, well, here I'm based on the fact that these composite fermion has a finite resistivity.
And why?
Well, here I'm assuming that it's either phonon or disorder that gives it a finite.
And disorder, that's fine.
Yeah.
But there was some finite temperature resistivity with T to 4/3 scaling, which is probably coming from electron-electron interactions. So is it kind of a...
It's from the gauge field effect, yeah.
Right, but is it a correction to, let's say, residual resistivity?
Over here.
Yeah, okay.
Yeah, so, well, I would say that at least the T0 part is coming from this
T0
extra.
is fine,
yeah, that's right.
What allows electron-electron interactions to affect the resistivity at finite temperature? You need to provide unplugs, you need to provide something else. So what is it here?
Well, it's basically my understanding is that the composite fermion can scatter off the gauge field, and then, well, I guess if you're worried about the drag effect, then it's not included in here.
Maybe this is due to the fact that they have two waves, and there is kind of friction between the waves.
Could you say that again?
Friction between the waves.
Going more into detail.
Yeah.
Especially where coefficient A is universal and doesn't depend on impurities, on phonons, and whether you can get it without looking at K and K prime that is together.
Ah, I see.
And if it's finite.
Right, yeah, so here this is, again, yeah, a good point that it's not considering the scattering between K and K prime yet.
That's not yeah. Okay, cool. Yeah, many points.
Yeah, okay.
Yeah, no, it's okay.
Who goes? Okay. Yeah, I'll be very quick. So I was just wondering for the stack of the conjugate composite Fermi liquid with superconductor, why should I think about the superconductor as decoupled? It should, in principle, affect the dynamics of the conjugate composite Fermi liquid, right? Because they're coupled to the...
They are coupled, right? They are coupled through the exciton tunneling here.
Yeah, but later on when you showed that you can get this bad metal...
I
meant the superconductor for the spin, not the superconductor for the electrons.
Oh,
the earlier construction that you had to get the bad metal in the first place. Yeah, this slide.
Over here, yeah?
Yeah, right here. Yeah, so why can't I just add the two conductivities without
sorry.
the dynamics
here,
exactly each
maybe
other?
I should clarify that. I'm saying that if on top of that you have some background XY model that is, in the symmetry broken phase, it's something that is not intrinsic to the conjugate composite Fermi liquid. Then it's kind of looking like two resistance in parallel. Then I'm adding the conductivity like that.
Okay, two more questions. Yeah.
Returning to this to the four thirds, right? The usual composite Fermi liquid just gallium arsenide. I don't think there is some very clear scaling of this resistivity at low temperature. Is there?
True. Yeah, we're going off just the standard gauge field calculation for that power. Well, this is the decouple.
I'm not talking about the superconductor. I'm talking about
I'm talking about the bad metal, right? So you're asking about the T to the four thirds. That's right. Yeah, right. So I'm saying the dynamics of gauge field is very different from composite liquid because actually we need to I think we kind of need to turn off this some kind of spin order, right? I think that can change the dynamics of the gauge field.
Well, can I?
One last question.
Yeah, but I can't resist mentioning because my whole talk was about how this T to the fourth third is incorrect. So, because it does not account for conservation of momentum, and when you put in disorder, you get completely different behavior that I discussed. So, I don't know, has this T to the fourth third been seen, or what are you using it for?
Right. Actually, yeah, that's a good point. So, yeah, I'm going off this old literature, and indeed, well, this could be replaced by other behavior, and I think the main message that you can take away is that the resistivity is going to decrease over as you increase temperature, because I think we could talk about how this can be modified, but the vortex resistivity is going to increase as you increase temperature. So, and then
At this point, thanks very much.
Yeah.